So we are going to be going over chapter 10, the last chapter, which is the chi-square and F distribution. Do you have any question on chapter 8 or 9?
Nope, not yet.
Okay. So the chi-square test and the F distributions are similar in the sense that they are based on degrees of freedom. We will use the chi-square test to test for independence and homogeneity, and we will use the F distribution to test for variance and for analysis of variance, which is also called ANOVA. So the chi-square is a distribution that we use in the past for confidence interval for variance and test for variance. And it is based on degree of freedom. It is a right-tail test. It is always positive. And we are going to use it to test for independence and homogeneity, as I mentioned. Let's start with this example. Innovative Machines Incorporated has developed two new letter arrangements for computer keyboards. The company wishes to see if there is any relationship between the arrangement of letters on the keyboard and the number of hours it takes a new typing student to learn to type at 20 words per minute. Or from another point of view, is the time it takes a student to learn to type independent of the arrangement of the letters on a keyboard. So we are going to do this test as an example of testing for independence. So H0 will be keyboard arrangement and learning times are independent. So generally, the null hypothesis for test of independence is that the variables are independent. And the alternative hypothesis is that keyboard arrangement and learning times are not independent. So a sample of 300 new students were taken and given and subdivided into three groups. The first group will use keyboard type A. The second group of 120 will use keyboard type B. And the third group will use the standard keyboard. So we can look at this table to see that 80 will use keyboard A, 120 will use keyboard B, and 100 will use keyboard standard. So the time it takes to learn to type 20 words is per minute is given here into three classes, 21 to 40, 41 to 60, and 61 to 80 hours. So 90 of the learners took between 21 and 40 hours, 150 took between 41 and 60, and then 60 took between 61 and 80. So within the cell, we have the number corresponding to each type of keyboard and the length of time it took to type, to learn the typing. For example, if we are here at the middle, it means 71 people learned how to use keyboard B to type in a range between 41 and 60 hours. So this is called a contingency table. It's like a matrix. And the main portion of it is this portion containing the number of time of intersection between the type of keyboard and the length of time it used to learn typing. So we will say that this is a 3 by 3 matrix because there are 3 rows and 3 columns. The last columns are the total, so we don't count it. So what we want to learn here first is how to determine the numbers that will be used in computing the test value. So to do this, I will go back to the whiteboard to remind you of a concept we learned in chapter 4, independence of events. We learned that the probability of A and B was equal to probability of A times probability of B when the events are independent. So if we have our contingency table, let me just use this simple one. Here is A1, A2, A3, B1, B2. So here we will have probability of B1, probability of B2, and then 1, probability of A1, probability of A2, and probability of A3. So here, for example, is probability of B1 and A2, the cell I just marked. So that probability should be equal to probability of B1 times probability of A2 in case of independence. Now, the probability of B1 and A1 is n of B1 and A2 divided by n of S, which is the total. And here is n of B1 divided by n of S times n of A2 divided by n of S. Look into what we have here. And what we are going to do is to establish the relation between the number of outcomes which is in a cell and the number of outcomes in the row and the column. And we want to establish that the number of outcomes in a cell, if there is independence, should be equal to the number of outcomes in the row times the number of outcomes in the column divided by the total. So you can see that here, that I'm working this side, n of B and A2 will be, there is n of S here, I will take it away. With this one, we can take those away. It will be n of A B1 times n of A2 divided by n of S. So what I am trying to explain here is that if there is independence, then the number of individual in a cell equals to the number of individual in a row times the number of individual in the column divided by the total n of S. I'm going to erase this table and rewrite it here as, we can say that if there is independence, let's call C1, let's call it CRS, the cell with the column with R and row with S, or row with R, let's say row with R and column with S, is equal to R times S divided by N, which is the total sample size. So we are going to use this rule to check when we have a contingency table. If it satisfies this condition, then the relation between the variable at the row and column are independent. Otherwise, they are not independent. Let's go back to the PowerPoint. And we are going to try one of the values. Okay, we will be looking at keyboard A and scale between 21 and 40. That's the first cell. Keyboard A and the scale between 21 and 40. Can somebody tell me how many people are in that cell? Keyboard A between 21 and 40.
25.
25. Now, if there were independence, if the two variables were independent, then the number 25 would have been 90 times 80 divided by 300. Can you use your calculator to check that? Row times column divided by 300.
Hold on, let me grab my calculator 1 second.
Yeah, get your calculator.
Okay, I have my calculator.
Yes. Please, everybody should do that.
What were the values again?
We are at the cell 1 with 25 values. And we are saying that if there was independence between keyboard and the time for learning, then this 25, the number at the place of 25 would have been 80 times 90 over 300. Can you do 80 times 90 divided by 300?
I got
24.
24.
Yeah, that's what I got too.
Is 24. So now we can see that they are not the same, almost the same, but not exactly the same, right? Let's look at cell number 8. I just pick another one. Number 8. What number do we see there? Cell number 8.
49.
49. Okay. Do row times column divided by total. What do you get?
I'm still calculating it out. Wait, so you do 49 times.
No. We are on cell 8, right?
Yes.
So that cell is in a row. What's the total of that row?
Oh, 150.
That cell is in a column. What is the total of that column? Number 8. What's the total for each column?
Oh, 49.
No, column. The column of where 49 is.
150.
150 is the total for that. I'm trying for you to understand what I'm talking about. So the column is 150, the row is 100. Do we get that?
Yes. Okay.
So
I feel stupid now.
so no, it's okay. We are learning.
I was kind of like thinking you had to like add all of them up, but like I didn't see that there was the row total and the column total.
Yeah, if you are not given, you have to calculate. You have to add them up. So total of column 150, total of row 100, multiply 150 by 100 and divide by 300. What do you get?
50.
50. You see that it is kind of close to the number in the cell, right?
Mm-hmm.
So just like we have been doing, this is from the sample. So the sample cannot be the exact value of the parameter. So there is a slight difference. And we want to know how significant that difference is by doing the chi-square test. So the number 25 you have here is called the observed value. Just like 30, 25, 30, all these numbers are the observed value, the value you get from the sample when you collect the sample. The values of 24 that we computed here, remember the first cell we say it would have been 24, is called the expected value when H0 is true. If there was independence, we should get 24 here, we should get 50 here. And you could compute those expected value for each of the 9 cells. So we are going to be speaking about observed value, which is what we get from the sample, what we collect. And then expected value is what we ought to have if the null hypothesis is true. So we are going to compute all the expected value. This is the formula for the expected value. Of course, we are going to use calculator at the end, so don't worry. But in case you don't have calculator, you should know how to get the expected value. So we now identify all those cells and then write down their observed value and the expected value. And here we take the difference between the observed and the expected value. So to find the test value, we will square this difference and add them up. So that will give us this formula, which is the test value. And this is a chi-square test. So once we have this, we can use either Excel or a table to identify the p-value, which is the area to the right of this value, chi-square. The degree of freedom is R minus 1 times C minus 1 for this test. So in this case, it will be 3 minus 1 times 3 minus 1 equals to 4. At alpha equal to 0.05, we can find either the critical values or the p-value to make a decision. So let's use our calculator now. So you all have a TI 83 or 84? If you have it, let's use it. Anybody has a calculator?
Yep.
Yep.
Okay, if you have a calculator, now these are the steps in using the calculator. You go to matrix. I want you to make sure that you can see matrix under X inverse. Second function, X inverse. Then you move to edit. And we will choose A, B, C, D, but let's choose A. You just press edit, you just press enter. Now, if you have not used your calculator for this kind of work before, you might have 1 times 1. Do you see something like that? Matrix A, 1 times 1.
Yes.
Yep.
So you have the list of matrix. We choose matrix A. That is where we are going to be working. So now change that 1 times 1 to 3 times 3. You just type 3 and then take your cursor to the other one and change it to 3. When you do that, you will have a 3 by 3 matrix. Are you there?
Yeah.
Yep.
So I'm going back to the beginning. So we are going to enter these numbers, 25, 30, 25, as it is arranged here. As you add 25, you press enter, then 30, enter, and 25, just as it is on this table. Don't enter the total. So you have the values in the calculator.
Yep.
Yep.
Okay, it's just like for this type of work, instead of line L1, L2, L3, you had matrix A, B, C, D, and we will be using matrix A. So now you leave there and go to start. You move to start again and go to test. And we will scroll down to C, letter C, chi-square test. Chi-square test. Then you press enter. What do you see?
It says observed A, expected B.
Yeah, keep it as it is. A where you enter your observe. When you enter in B, it compute the expected and put it in B. But we don't even need to know what is there. So you just go to calculate. So don't change anything there. And press enter. What is the test value? Chi-square.
13 point,
Yes.
13.3.
13.3. That is the test value. And what is the p-value?
0.0098.
Yes. So we will compare this p-value to alpha, which is 0.05. What should you think should be our decision in comparing this p-value to 0.05? When p is less than or equal to alpha, we reject the null hypothesis. Otherwise, we do not reject the null hypothesis. So what decision do you think we should take here? We reject or we do not?
Reject.
We reject the null hypothesis because p is less than or equal to alpha. Now, the null hypothesis was keyboard and learning time are independent. So if we reject it, then our conclusion will be there is enough evidence to reject the claim that keyboard and time of learning are independent. Because at the beginning of the problem, the question was, are keyboard arrangement and learning time independent? So this test led us to rejecting the null hypothesis, which was actually the claim. The claim was keyboard and learning time are independent. So we reject it, and we will now say there is enough evidence to reject the claim that keyboard and learning time are independent. Is that okay?
Yes.
Yep.
Okay, we will do another example. In this example, we call it test of homogeneity, but it's the same thing as the test for independence. So there is homogeneity when the distribution of proportion are equally likely, kind of, are the same. For example, Are the preferences of pet by males and females the same? We may have a question like that. Tim is doing a research project involving pet preferences among students at his college. He took random samples of 300 females and 250 male students. Each sample member responded to the survey question, if you could own only one pet, what kind would you choose? The possible responses were dog, cat, other pet, no pet. And we have the sample here. So what I want you to do now is to enter this in the calculator as a matrix. You remember you go to Are you able to put it into the matrix?
Yes.
Yes.
Everybody? Okay. So just follow the same thing steps. After matrix, you go to test, choose chi-square test, and then we will move having the results. You will have the results at hand. So this is a 2 by 4. Anyway, you will be seeing it each time you are trying to enter the values. Just try to make sure you can enter all the values. Do you have the test value?
Yes.
What is it?
16.059.
Okay, good. So that is the p-value for comparing the proportion of males and female preferences of pet. We are going to use a 1% level of significance. I want you to know that test of homogeneity, the null hypothesis is each population share respective characteristic in the same proportion. This is generally what you will see from the questions that you have. Like in this case, the null hypothesis will be the proportion of females and males naming each pet preferences are the same. The proportion are not the same in H1. So we use the calculator to get the test value 16.06 and the p-value 0.01. The degree of freedom is R minus 1. The number of row was 2. 2 minus 1 is 1. And then C minus 1. The number of columns was 4. 4 minus 1 is 3. So 1 times 3. Since the p-value is less than alpha, we reject H0 at the 1% level of significance. So the conclusion will be that there is not enough evidence to reject the claim that male and female students at Teams College have the same. There is enough evidence, to reject. We reject H0, which was the claim. This is not correct. There is enough evidence to reject the claim that males and female students at Teams College have the same preferences when it comes to selecting a pet. So essentially, for the test of independence and homogeneity, you will use a matrix to compute the chi-square test value and then get the p-value to make a decision. And H0 is generally the independence. The variables are independent for independence, and for homogeneity, the proportions are the same. So another test that we use for the chi-square is the goodness of fit test. The goodness of fit test uses the chi-square distribution with the to determine if two populations have the same distribution. We want to determine if two populations have the same distribution. I will explain it with this example. Last year, the labor union bargaining agent listed 5 categories and asked each employee to mark the one most important to her or him. The categories and corresponding percentages of favorable responses are shown in the table. So last year, it was determined that 4% like vacation time, 65% like the job because of the salary, 13% because of safety regulation, 12% because of health and retirement benefits, and 6% because of the overtime policy and pay. So this was the distribution of workers' preference last year. So we may want to know, are workers this year having the same preference as those last year? So the procedure will consist of taking a random sample of workers and then interview them and find a proportion that like vacation, salary, safety regulations, health and retirement benefit, and overtime policy. And we will compare the observed value. The observed value is what you get from the sample with the expected value. The expected value is what you get if H0 was true. That is, if the distribution this year fits last year's distribution. So H0 will be the population fit the given distribution, and H1, the population has a different distribution. So the test value is computed in the same way, but the degree of freedom is different. The number of category here is K, so the degree of freedom is K minus 1. For the example of workers here, the number of category here is 5. So the degree of freedom will be 5 minus 1, that is 4. So H0 will be the present distribution of responses is the same as last year. And H1, the present distribution of responses is not the same. So the sample we have has 500 individuals. So the expected value will be computed by taking the proportion of those 500 that correspond to last year's distribution if they were the same. So for example, vacation time was 4%, and 4% of 500 is 20. The number of people that prefer vacation time this year is 30. 65% of 500 is 325. Last year, there were 290. I'm sorry, this year there are 290. So we want to compare the observed values that we have here to the expected value to find the test value. So we can use calculator again, but at this time, I don't know if, can you, to use this test, let me see if I gave you the, you go to start, edit, and write the observed values in L1 and expected values in L2. So we go to start. I hope you know how to clear the values in your calculator. Clear values in L1 and L2, and now on L1 you enter the observed value. Are you able to enter the values in L1 and L2?
Yep.
Yep.
So you go to test and choose D, which is chi-square goodness of fit, GOF. So the degree of freedom here is 4, and we calculate. There's nothing much to do there. You have the chi-square test value.
Is that 14.15?
Yes. So you can see it here on the PowerPoint. I want you to remind you again that the expected value here is obtained by using last year distribution together with the sample size. Last year distribution was given as a proportion. Multiply each category proportion by the sample size to get the expected value. So on the calculator, you enter the observed value and the expected value. So the p-value is 0.06. We compare it to alpha. I don't know what was alpha here. Alpha here is 1%, and we see that p is less than 1%, 0.01. So we reject the null hypothesis. By rejecting the null hypothesis, we will conclude that there is not enough evidence to support the claim that last year's distribution is the same as this year's distribution. I want you to observe that so far we have been using reject, reject, reject on our conclusion because our claim is generally on H0. The variables are independent, the variables are homogeneous, the distribution are the same. So on the conclusion, we are going to be rejecting, rejecting, rejecting. Are we good at this point?
Yep.
Yep.
So essentially, what you will be doing is know which type of test you are performing. If it is a test of independence, it's the chi-square test with matrix. Independence and homogeneity, you use matrix. Goodness of fit test, you use the distribution to determine the proportion that is going into expectation. So we are going to quickly go over 10.3 and 10.4, which are tests of variance and uses the chi-square. I usually don't ask you questions about this except maybe to find the test values. And so here is again the chi-square distribution that we use to test for variance and standard deviation. So your calculator can be useful in finding the probability that using the chi-square distribution. I want us to practice that for a moment. We can use Excel, we can use calculator. Let me see what we have here. I'm going to practice that when we are. So let's look at this question. In testing the variance or standard deviation, we use the chi-square distribution with degree of freedom n-1. Find the chi-square value such that the area to the right of chi-square is 0.05. Use degree of freedom 10. So you go to second function, distribution, and number 8 is chi-square CDF. CDF is, when you see CDF, it is about the left tail. So let's practice that. You press enter. Do you see what I'm talking about on your calculator?
Yep.
Yep.
Yeah, second function, distribution, number 8, I think. The lower value is always 0 because it is a non-negative distribution. The upper value is this is for probability. I'm sorry. Do again, second function, distribution, and choose 9. Oh no, there is no inverse here. No, your calculator does not have chi-square inverse. So we will use Excel. What about that? I see the reason why I put Excel here. Can we use Excel? Do you have Excel?
Yeah. Yeah.
Okay. So let me go to Excel. I have a lot of sheet here. You choose any cell and put equal to. As you start typing chi-square, Excel will offer you several options. If you choose chi-square inverse right tail, if you choose chi-square inverse, it will just give you for the left tail. If you remember, the question we had was for a right tail. Let me go back again for you to understand what I'm talking about. In testing the variance or standard deviation, we use the chi-square distribution. Find the chi-square value such that the area to the right of chi-square is 0.05 with degree of freedom 10. Do we understand the meaning of me saying right?
Yep.
Are we together?
Yep.
So we have 0.05 is to the right of chi-square, and we want to determine this value, chi-square, with degree of freedom of 10. So now I will go back to Excel. So we will choose chi-square inverse, right? We do inverse because we have the area and we want the value. When you have the value and you want the area, you do probability, and that your calculator could do that. But when you have the area, which is the probability, and you want the value, then you choose, because it was right, you choose right. So this is how you know what to do. You will write the area, which is the probability, 0.05, and the degree of freedom, 10. Can you do that? What do you get? Are you lost?
I got the same answer as you did.
Good. So, because it was the right tail, if I was to use just chi-square inverse, if I want, I can still use chi-square inverse, but I will put 10 here, I'm sorry. I will put the probability here, 0.95 and 10, because I am thinking about the left tail. If the right tail is 0.05, the left tail is 0.95. Do we understand that?
I'm having a tricky time entering it into Excel. I can get the options too, but then the values, it's acting funky.
So, well, what does it tell you?
It just shows up that number sign and then it just says name in all caps with a question mark. Like an error happened.
Let's do this second one together.
Thank you.
Let's find the left of the chi-square. The area to the left is 0.05. What will be the degree of what will be chi-square? If the area to the left, can you see the PowerPoint?
Yes.
So this area to the left of chi-square is 0.05. We want to know what is chi-square. So let's go back there. I will write equal to, and then I will start CH, and CH, I'm trying to write chi. So we will use inverse. Remember, all along, we have always been saying that by default, whenever we have area, if there is no specification, it's the left area. If you are using the left area and you are given the right area, you need to make sure you get it to the left by subtracting it from 1. But Excel also gives us the option for chi-square inverse for right tail. So because this question was for a left tail, I'm going to choose chi-square inverse. Are we all there?
Yes.
That's where it gets tricky. Once I click it, it does not show up the same.
I think you have to like double tap on it. Or like maybe press enter.
Oh, double tap. Thank you. Got it now.
You're welcome.
Awesome. Thank you.
Okay, thank you. So remember, our question is to find the chi-square so that the area to the left of chi-square is 0.05 and the degree of freedom is 10. So I'm going to type 0.05 here and the degree of freedom of 10. So I usually give you this type of question on the quiz. Find chi-square so that area to the left is 0.05, degree of freedom of 10. I can say sample size 11. If the sample size is 11, the degree of freedom is 10. We might have to exceed the time again today. So when it is time and you feel like going, you can go, but I would prefer to finish chapter 10. So, but I will try to go a little bit faster. Now that you have understood this, we are going to move quickly on. So the test value in testing for the variance is n-1 times s squared over sigma squared. N-1 is the degree of freedom, s squared is the sample variance, sigma squared is the hypothesized variance. I generally ask you on the quiz to find the test value. So if you want to find the p-value, if it is a right tail test, you can use your calculator to find the chi-square distribution, right, left, to find the p-value, or you can use Excel. But I generally only ask you questions about finding the critical value, that is, find the chi-square value so that the area to the left, the area to the right. For the confidence interval, this is the formula for confidence interval. N is the sample size, S square is the sample variance. Now, what is chi-square U and chi-square lower? So chi-square U is the right tail for the area at 1 minus C over 2 when C is the confidence level. Okay, suppose you have a confidence level of 90%. What we are saying is that if you have a confidence level of 90%, then subtract it from 1 and you have 10%, divide it by 2 and you will have 5%. 5% will be for the right tail, that's the upper part, and 95% will be for the left tail. And you will have, let's do this example. A random sample of 30 green bean plants has a sample standard deviation of 3.4 days for maturity. Find the 95% confidence interval for the population variance sigma squared. Assume the distribution of maturity time is normal. So C is 0.95. We are going to subtract it from 1 to get 0.05, then divide it by 2. All what we are looking for is, I will show you that on the whiteboard. So this is an idea of how the chi-square distribution is. So if C equal to 95%, we will have a chi-square here and a chi-square here. Some people call it chi-square left and chi-square right. So alpha is equal to 0.05. Because there are two tails, alpha over 2 is 0.025. So this tail is 0.025. And this tail is 0.025. The chi-square is generally a right tail. But if you are using Excel, Excel will make the distinction when you are using right or left. So we want to know what are these two numbers. We go to Excel. And we type equal to chi-square. Chi-square distribution right will give us the value for the right tail. That right tail was 0.025. 0.025. Hope I forgot the degree of freedom. N was 30, so the degree of freedom is 9. I'm sorry, 29. So we will write 29 here. So 3.94. I'm not sure I did the right thing here. Equal to chi-square distribution right tail I'm looking for. I'm sorry. We are looking for the inverse. We have the area 0.05, 0.025, 29. So this is the upper value with the right tail of 0.025. Then now let me do for the lower value. It's still chi-square inverse 0.025. You will see that I am actually typing almost the same thing, but with different results. It's not the same thing I am typing. You see, if I want the chi-square inverse for right, I will choose this, I enter the right tail. If I choose chi-square inverse, I put still 0.025 and it's for the left. When there's no specification, the area is left area. If the area is right area, you will be see this RT. Can you guys get this 45.72 and 16.04? Can any of you get it?
I was able to get the 16, but I couldn't get the 45.
Pardon?
I was able to get the number below it, the 16.047, but I wasn't able to get the 45 value.
Okay, let's do the 45 again. You type equal to chi. 45 is the upper value. You remember that when I made that table, there was an upper and a lower. The upper value, the tail of the upper value is 0.025. The area to the lower value is 0.025. But on Excel, we want to know that the upper one is the right. So I will choose chi-square inverse right. Then the area is 0.025 and the degree of freedom is 29. Can you do that?
Yep, there we go. Thank you.
You're welcome. Okay, so we are able to get the chi-square upper and chi-square lower. Sometimes I call it chi-square left, chi-square right. I like the right so that you know you are choosing the right tail. So now into this formula, we fit those two numbers. The standard deviation was 3.4. You square it and divide by 45.72 and get the confidence interval for variance. The confidence interval for standard deviation is obtained by taking the square root. So I know this can be a little confusing, so I don't ask you a lot of questions on the variance and standard deviation. But essentially, using the chi-square, you want to be able to find the chi-square left, the chi-square right, or upper and lower, which you were supposed to read it from the textbook because I developed the habit of not using the tables. That is why I want you to see how to get it from Excel. Testing two variances. Sometimes when we were doing the t-test for two samples, you were asking me about pole. And you asked me if we should use pole or not. I was saying don't use poll because we cannot show if the variances of the two populations are the same. So we can do the test for variance using the F distribution to compare two variances to know if one of the variance is bigger than the other. That's essentially what the two variance test is about. We use the F test, which is similar to the chi-square with the difference that it has 2 degrees of freedom. The degree of freedom of the numerator and the degree of freedom of the denominator. In making a F test for variance, we choose the numerator to be the variance, the larger variance. The sample with the larger variance is the numerator. The sample with the smaller variance is the denominator. The degree of freedom of the numerator is n1 minus 1, and the degree of freedom of the denominator is n2 minus 1. So these are the type of tests. We only do either a two-tailed test or a one-tailed test. Even as we are doing the two-tailed test, all what we do is that to make it as if it is a one-tailed test with half p-value or half alpha. So most of the time you will have either to choose either a sigma 1 square is greater than or equal to sigma 2 square. That is the first population has the larger variance. But sometimes you can also have to deal with a difference. Remember that when you are dealing with a difference, you can consider it as a one-tailed test with half level of significance or double p-value. So this is not a difficult thing to do. We are skipping reading table. It's really even more confusing. So this is how we do about it. If you have data, you enter it in L1 and L2 and choose two sample F tests to complete the test. Let's do an example. Because of time, I will just speak about this example and we will do it. Here in this example, we want to compare the variation of diameters of pipe made with ceramic and pipe made with stone. Naturally, we expect that pipe made with ceramic can vary more than pipe made with stone, because to curve a stone is harder than to make it with a pipe. So the data are given to us here, and we want to test the claim that ceramic pipes varies more than stone pipes. Do we get this? Ceramic pipes varies more than stone pipes. So let's enter the data into the calculator. We will enter it in L1 and L2. Do you have the data in the calculator?
Yes.
You enter it on L1 and L2. Now we go to start, then test. You can start from the reverse to easily get to there. Is E, two sample F tests. do you see the test?
Yes.
Two sample F test. So we use data. If we were given this, the statistic as it is here, we will use statistic and enter the statistic that are here. Make sure that you pay attention to enter variance when you are asked for variance and standard deviation when you are asked for standard deviation when you are using statistics. So what is the test value F?
$4.499.
1.49. And the p-value? And the p-value?
0.0436.
No, you choose different from. So to change it, just go back to start. Two sample F tests. Now we use data, so we will go to L1, L2. We have data. And when you see sigma 1, choose greater than sigma 2. You see what I'm talking about?
Yes. Yep, now I got it. So F is 4.49 and then P is 0.021.
Good. Alexis is not saying anything. Are you with us?
Yes, sorry.
You're all with
I was
us?
calculating it when you guys were talking.
I know. Maria seemed not to be saying anything. I hope you are following us.
Yes, I am.
Good. Okay, please be patient with me, maybe about 10 more minutes for us to finish. I like when you are there because it's more like a conversation rather than me just explaining and just moving. But if anyone has an emergency, feel free to go. So you use calculator this way, either entering data or using statistic as we were doing before. So with this p-value of 0.02, it is less than 0.05. So we do not reject, I'm sorry. It's less than alpha, so we reject 80, right? Less than alpha, reject 80. So there is enough evidence to support the claim that ceramic pipe varies more than stone pipe. You know, to make clay is much easier, so people will make more different sizes than when they are using stone. That's essentially what we are saying. So you will practice with your homework. Remember, it's the F test. It has only right tail and two tail. But you choose, because you are using your calculator, which test to use. Is much easier with the calculator. Last section, the ANOVA, analysis of variance. This section is kind of the most important of this course, the easiest because we have already learned so much. That's why it becomes easy now. Otherwise, it would have been the most difficult part. So remember that in chapter 8 and even 7, we were comparing two population mean, two population proportion. Sometimes we want to compare more than two population. And when we want to compare more than two population, using a t-test, as we were doing, will be much more cumbersome. And for that reason, we may want to use one test that can compare like more than two population mean. The F test for analysis of variance just does just that. So I will start with an example. I mean, as I have been doing, because it's much easier to do it with an example. A psychologist is studying the effect of dream deprivation on a person's anxiety level during waking hours. That is, you want to know, when you wake somebody, does that make that person more anxious the next day? So what will happen here is that three groups of people are going to go to sleep, and then they will be woken up at different times, and their level of anxiety will be measured, to summarize what the example is about. So our question is, do they have essentially the same level of anxiety? So we have 3 groups and we want to test whether the mean level of anxiety for the 3 groups are the same. They were waking up at very different time. So the null hypothesis for the analysis of variance is mu1 equals to mu2 equals to mu3 equals to as many population as you have. Where you will be trapped on your quiz is the alternative hypothesis. You don't put different here. If they are not all the same, the opposite of it is that at least 2 are different. Do we understand what I mean here? To say that they are not the same is enough to have 2 that are not the same. You don't necessarily need to have different from each other altogether. So at least 2 of the means are not equal. So to achieve this, we are going to use the formula of variance. In the formula of variance, we generally take the sum of the variation divided by the degree of freedom. And the sum of the square of the variation is this. We did this in chapter 3. Not a big deal. So we are going to determine 2 comparisons. We are going to compare 2 things. We are going to compare the variation between the groups and the variation within the group. In the variation between the group, we will take the sample mean for each group, compare it to the sample mean of all the sample put together. That's the mean total here. We subtract it and we multiply by the sample size, square it and add them up. Don't worry much, we are going to use calculator, we are going to use Excel. But I want you to know what are the numbers that you see on Excel. So we put, if we have 3 samples, we put all of them together, as you can see on this table. So these are the 3 samples. When we take the sum of them, we have 38 on group 1. We have 61 on group 2. And we have 57 on group 3. When we add them all, we get the sum of the total 156. Now the sample size were N1, N2, N3, N4. N1 was 6, N2 was 7, N3 was 5. When we add it, we get the big sample size, 18. So we are going to use those and try to say that if they have the same mean, then we can find the sum of the square between by subtracting the sample mean of each group from the big sample mean, square it and multiply by the sample size. When we add it up, we call it the sum of the square between. And we will have also to deal with what we will call the sum of the square within. The sum of the square within consists of taking each group and finding the sum of the square of the deviations as if we want to compute their variance for that group. So that is what is going to give us the SSI, that's the sum of the square within. Now, the mean sum of the square between and the mean sum of the square within are obtained by dividing the sum of the square between by their degree of freedom. The degree of freedom for the numerator is k minus 1. K is the number of groups, like we had 3 groups there, k will be 3. And n minus k is the degree of freedom for the denominator, which is big sample minus number of category. So the test value is mean of the square between divided by mean of the square within. At this point, let's use Excel. We can use calculator. Calculator is good, but it's not very professional, as you can. I want us to use Excel. Calculator is much easier to use, actually. Excel is also easy. So please, let's use Excel. Are you guys on Excel?
Yep.
So I'm going to enter, let me put here X1. I don't usually do this. I don't usually do the title, but you don't have to do it, but I'm putting it so that you know what I am actually writing here. On X1, I will enter the anxiety level for the first group. 9, 7, 3, 6, 5, 8. On X2, I will enter the anxiety level for the second group. On X3, anxiety level for the third group. If you go back to the text, you will see that actually they wake somebody up sometimes when he just started having the dream. They wake another person at the middle of the dream, and they wake another group, they wake them up at the end of the dream. So it's not just like waking them anyhow. At what point do you wake somebody? That will help to determine if that will affect his level of anxiety. Okay. Do you have the data on Excel?
Yes.
Everybody, Maria, okay. Maria, are you using Excel?
Yes, I am.
Good, thank you. So you could have 10 groups for different type of situation. Bottom line of what we have learned so far is that if we have 10 samples from 10 different population, we can compare to determine if those 10 samples are coming from population with the same mean. That's the meaning behind the analysis of variance. I don't tell you read all through the PowerPoint, but generally we expect the population to be normally distributed. We expect the population variances to also be the same. So those are the main conditions for analysis of variance. So we are now going to go to data analysis. And we will choose, I think is the first one, ANOVA single factor. ANOVA single factor. So look at what I'm going to do. Our data starts from row 1, column 1, column A. I highlight where our data is from A2 to C8. Can you do that?
Yep.
Okay. So, and I click output range. You have done this before. And I just choose anywhere I want the result to be. Then okay. So this table gives us several information. We have the mean from group 1, 6.33, the variance from group 1, 4.66, mean for group 2, 8.71. So when you use ANOVA, you have a lot of information. If you had 10 groups and you wanted to find their mean, the variance, you can just use ANOVA and then pick those ones that you are interested in. So now, the sum of the square between, I want you to know how to read. Sum of the square between group is this one. This is the sum of the square between. Can you see it? Sum of the square between.
Yes, I can.
And this is the sum of the square within. These are the degree of freedom, 2 and 15. 2 for 3 minus 1, 15 for 18 minus 3. I'm sorry. Yeah, 18 minus 3, and minus k. This is the mean of the sum of the square between, is the mean of the sum of the square within. Essentially, the distribution is an F distribution. So the test value is 8.21. and the p-value is 0.0039. So you know that when we are conducting a hypothesis test, the most essential information we need is test value, p-value. If alpha is 0.05, what should be our decision here? For alpha equals to 0.05, what should be our decision?
Would we reject?
Reject the null hypothesis. Reject the null hypothesis. So our conclusion will be, depending on the claim that we had, this population don't have the same mean. Or sometimes you will be asked, are these samples coming from the same population? If somebody asks you that question, it means, are these samples coming from if they come from the same population, that means their mean are the same. You could say the samples are not coming from the same population. So we can say that actually the time you wake somebody up affects his level of anxiety, because we rejected the null hypothesis, which say there is no difference. So if we reject the null hypothesis, that means there is a difference. Level of anxiety is not the same, depending on when someone is woke up. So what you want to, actually that is it with this section. I don't want to keep you much longer. So if you are using your calculator, just 1 minute. If we are using your calculator, of course, you will enter your data in L1, L2, L3. Then you will go to test. Is the last one, ANOVA, and you choose ANOVA. Then when you choose ANOVA, a bracket will open for some of you. Or you just enter L1, L2, L3, and so on. Do you understand what I'm trying to say here? You can use Excel. Excel is just best. I prefer you use Excel. But if you are using your calculator, you enter your data in L1, L2, L3, and you choose the last option, which is ANOVA. When you choose ANOVA, to type L1, you say second function 1, comma, second function 2, comma, and second function 3, comma. And then you close the bracket. That will give you the ANOVA. If you really want to learn more detail about it, you can go over the PowerPoint again. It's always there on Canvas. I try to explain the aspect of it that I know you need to understand, because by reading on your own, you will not be able to understand. Yet, if you have any question, try your homework from today. If you have question, send me an email. If you need more help, we can meet on Zoom. At that time, I will not need to record, and we can spend 1 minute or 1 hour, and when you have questions, okay?
Great, thank you so much.
You are welcome. Hope some of you will be in face-to-face class from Monday.
Yes.
Okay, see you on campus soon.
Yes, thank you so much.
You are welcome. Please, if you have questions, send me an email.
Well, thank you so much. Have a good evening.
You too, thank you.
Bye.
Bye.